Today we'll be presenting about our KDR presentation, and in my group we have myself, Kiara, and Jason. First, I'm gonna start talking about the propeller. A propeller is exactly like a wing. It does have a horizontal force and a vertical force. But instead of calling them lift and drag in a wing, on a propeller we call them thrust and torque. We have two types of propeller. As we can see, on a 172 we have a fixed pitch propeller, on a 182 we have a variable pitch propeller. With fixed pitch propeller, it's a manufacturer that sets the blade angle and then hence sets our aerodynamic force caused by the propeller, and it cannot be adjusted during flight. Or else on a 182 we can change the pitches of the propeller as we need throughout the flight. Starting off, this is an example of a variable pitch propeller which can be adjusted during flight. What happens is, this is a fine pitch. This is mostly used during high RPM and low speed. So en route of a climb or a descent, when the propeller has to rotate at a high RPM, the pilot in command will be fining the propeller to a fine pitch, allowing the propeller not to overspeed and to fly at a slow speed. Once we coarsen the pitch, this will then allow the aircraft to fly at a lower RPM but at a higher speed. So for example, once an aircraft travels off from a climb, it will coarsen the pitch to allow for a slower RPM and a faster cruise speed. And that's one of the benefits of having a variable pitch propeller. This is an example. If a fixed pitch propeller that's been decided by the manufacturer can either be a climbed pitch or a cruise pitch. That's with a fixed pitch propeller. Whereas a variable, it can be either and or. If the manufacturer decided to set the propeller as a climb pitch propeller, it would be only be most efficient during low airspeed and high RPM. Whereas if it's a cruise pitch propeller, it will be most efficient during high speed and low RPM. Whereas with a constant speed unit or a variable pitch propeller, you will have a high efficiency throughout the flight since the propeller pitch can be adjusted as needed.
In my part, I'm talking about engine with a constant speed propeller, and they are operate at a high manifold pressure, low RPM, and a low manifold pressure, high RPM. And in this part, cause a constant speed propeller, the pilot can adjust the propeller's RPM and the manifold pressure. So if the pilot can set the correct manifold pressure and RPM speed, and they will have a good efficiency for the fuel flow. And next one, let's talking about high RPM and low manifold pressure. If a pilot setting for the higher RPM, they will have a low manifold pressure. Cause a low manifold pressure, they will have a low engine's output. That means they will have a better fuel efficiency, but because of higher RPM, so they will produce more power for the aircraft. High manifold pressure and low RPM. In this case, because of low RPM, that means the aircraft they don't have too much power, and high manifold pressure, and that's more engine output and more engine power, so they will burn more fuel, so the efficiency will be worse. And because a higher engine output, more engine work, they will produce more temperature for the engine, and in this case that may cause a detonation due to a high temperature for the cylinder temperature. The blind angle is the angle between the aircraft rotation and propeller's call line. And on the whiteboard, this one is aircraft rotation line, and here is a Brad call line. If we increase the RPM, that means the Brad angle will be increased. But when we decrease the RPM, the Brad angle will decrease as well. And in the another condition is we increase the RPM. For pilot increase the RPM, the pitch will be fine pitch. But if a pilot decrease the RPM, the pitch will become a core pitch. They will become further away from the aircraft rotation line. Next part is about helix angle. The helix angle is a propeller rotate through the reactive air. And this line is a rotation of the plane. And here is a Brad angle. So the helix angle is the red line. That's the propeller goes through the airflow. So this one is a helix angle. And in this diagram, that's showing the difference of angles of propeller. You can see that this one is a coarse pitch, and this fine pitch. And if the aircraft landing and want to reduce the speed, they will reserve the propeller's angle to reduce the speed. So that's a reverse angle. The next part is about thrust. Because the propeller they are working, they will produce area which is a low pressure area in front of the aircraft, and the propeller they will suck the air inside and produce a high pressure at the rear of the propeller. And if the pressure from higher to low, that will make the aircraft move forward. That is a thrust. Next one is about torque. Because the engine gives power for the propeller, and refer to Newton law of reaction. If you give a force for item, and they will give reverse force to another one. So if engine give a force for the propeller turning to a right, that means they will have another force turning back to a anti-clockwise. So the aircraft will rolling to a left. And in this case, like a pilot doing a takeoff power, they will have a lot of power for the engine, and aircraft will rolling to a left, and we will press the right pedal to rolling aircraft to a right. So that's a torque.
I will be talking about normally aspirated and turbocharged engines. Here we have a normally aspirated engine, which means it takes the air basically from the outside. So as a normally aspirated engine climbs from sea level at a particular fixed throttle setting, it loses its energy as the density decreases in the air as you increase altitude. It is still capable of producing full power, but because of the air density decreasing, it lacks the amount of air it needs for it to be able to produce a certain amount of power, and it struggles. To compensate for this lack of power, the air is pumped into the inlet manifold, or air intake. It then goes through the centrifugal compressor, which is here, and then it is sent out through there. The extra air that the compressor generates allows the engine to burn more fuel and create more energy. It also it doesn't increase the amount of power that can be generated, but it allows the power to be maintained throughout a climb, which is commonly referred to as normalized. Turbocharged engine uses a turbine as a power source to drive the impeller. Rather than using fixed gears like a normally aspirated engine, it uses engine power directly to drive the compressor, which is here. So exhaust gases from the engine produce kinetic energy, which is then used and directed to turn the turbine within the system. So it'll come out through here, it'll go into the turbine, that'll spin it, and it'll go into the compressor, and it'll be a lot more air being produced. The main purpose of the turbocharger is that it will produce a boost which will maintain desired manifold pressure at a given throttle setting, regardless of the altitude or the ambient air temperature and pressure. However, this can only be maintained until a critical attitude, and manifold pressure can then no longer be maintained, which means the aircraft has reached its critical altitude. Energy from the turbine is then delivered to the compressor through a system of gears and a wastegate in the exhaust system, which dictates how much gas is sent directly over and how much is actually sent to the turbine itself. So when the wastegate is in an open position, it'll direct all its gases overboard with none actually going through the turbine. The exhaust gas will come through here and go out rather than going up through here. When the wastegate is in an open position, it directs all the gases overboard with none actually going through the turbine. This causes the turbine to freewheel, and then the engine will act as though it's a normally aspirated engine. But when the wastegate is in the closed position, more of the exhaust gas is directed over the turbine, and that increases the impeller's speed, which then boosts the manifold pressure. An advantage of the turbocharged engine is that the compressor doesn't do anything until the throttle butterfly is actually wide open, and that's when the wastegate can be closed to direct the exhaust gas through the turbine to drive the impeller.
I'm gonna speaking about brake horsepower and thrust horsepower, and about the useful energy that's been produced by the piston and how much is actually being used to actually drive the propeller. First things first, I'm gonna be talking about the brake horsepower. What we know is that it is almost impossible to get 100% efficiency due to various reasons. As the piston burns the fuel-to-air mixture in the cylinder, we have around 40% of the energy lost through exhaust, and this is unavoidable. We are now remaining with 60% that is yet not completely used as useful energy. A further decrease in energy is lost to the heating components of the engine. As the piston energy burns up, pushes the piston down the cylinder, which produces heat that then increase the further loss of energy. Not only that, but what's remaining of the 40% is then 10% more is then lost to friction due to the barriers between the pistons in the cylinder and the inlet manifold, which is then being reduced due to the oil between the piston and the cylinder in the engine. Here is an example for brake horsepower image. We have a fuel to X mixture here inside the cylinder where it's been burned. We have 40% lost through exhaust, and we are left with 60%. 10% is lost through the friction because of the engine, because of the piston and the cylinder wall, which is then can be reduced due to oil barriers between the piston and the cylinder. The remaining of the energy that is then can be used as useful energy is called brake horsepower. This energy is used then to push the cylinder downwards that then helps turning the crankshaft to the aid of the connecting rod. But as the brake horsepower pushes the crankshaft in order to spin the propeller, that 30% of energy is still not 100% efficient. One of the reasons that we lose energy in the process of turning the propeller is because the propeller, since it's exactly like a wing, it has the aerodynamic forces, and if like a fixed pitch propeller like in a Cessna 172, we won't always have the most efficient lift to drag, hence furthermore of the energy can be lost due to the drag cause. And the friction between the crankshaft and the propeller, the gears driven, there is a furthermore loss in energy. After all the energy lost due to the aerodynamics forces, the friction between the engines, the energy that's left to actually produce thrust is called thrust horsepower.
Asymmetric blade effect is a yawing moment which is caused by a high angle of attack of the propellers. So when the blades are at a higher angle of attack, the downgoing propeller is at a higher angle of attack than the one that is going back up, and this generates more thrust, and that's what causes the yawing moment because it's overpowering to one way. With a propeller that rotates clockwise, it will then cause the aircraft to yaw to the left. When the aircraft is moving horizontally, so forward, the direction of the airflow is different on each side of the propeller disc. During the takeoff run of a tailwheel aircraft, while the tail is still on the ground and the propeller shaft is inclined upwards, the plane of rotation of the propeller is tilted rearward. Because this only takes place when the propeller disc is inclined to the relative airflow, once the pilot lifts the tail, the disc will then be close to more of a right angle, and the relative airflow and the thrust line will move back to the centre of the disc, and the yawing moment will be reduced. In a nose wheel aircraft, there is little or no asymmetric blade effect at all, because the aircraft is at a level attitude to begin with, and meaning the up and down going blades rotate at the same distance in the same time, and the angle of attack are the same as well.